Welcome to Unit 2. In this unit, we're going to be learning all about how to solve all different kinds of linear equations. And in this first section, we are just going to dive into the basics of solving linear equations. But first, before we do that, we need to understand what exactly an equation is on its own, and then how to determine if we are dealing with a linear equation or not. So an equation is a mathematical statement that is separated by an equal sign. And this equal sign is stating that both sides of that equal sign are equivalent to one another. And then a linear equation is a specific equation that contains a variable. However, this variable cannot have any exponents attached to it. So to get a better idea of what a linear equation looks like, let's dive into our first example. So for example 1, let's determine if the following are equations, and if they are equations, determine if they are linear or non-linear. So for example number 1, we have 13 equals 13. Well, we have an equal sign, so that must mean that we for sure have an equation going on. So this is an equation. However, there's no variable or letter in this equation, so this is nonlinear. For example number 2, I encourage you to pause the video and try this one on your own. And assuming you have given it a go, let's work through it. So we have 2 plus 4 equals 4 minus 2. Well, there's an equal sign, so this is for sure an equation. However, one thing to note here is that if we do the math, 2 plus 4, that's 6. We're going to say that's equal to 4 minus 2. Well, that's 2. 6 doesn't equal 2, right? So this is what is called a false equation. So this is an equation, but it's false. It's not a true equation. So you can say this is a false. I'm going to say false equation in parentheses. And then we have to determine if this is linear or nonlinear. Well, looking at the equation, I can tell right away that this is nonlinear because there's no variable or letters in this equation. So we're going to say this is nonlinear. Looking at example 3, well, we have an equal sign, so we know this is an equation. And looking at this equation, there is a variable, there's a letter, and we don't visibly see any exponents attached to this variable, so this is a linear equation. And in fact, in this section of notes down here, you're going to learn how to solve these kinds of linear equations that you see here. For example, number 4, we have 7x. Well, there is no equal sign, so this is not an equation. Not an equation. Specifically, it's an expression. What we have here is an expression. Alrighty. For example number 5, we have 7 equals x cubed. Well, we have an equal sign, so this is an equation. However, that x is cubed. It has an exponent attached to it. So this equation is nonlinear. And then looking at example 6, I encourage you to pause the video and see if you can try this one on your own. And assuming you have given it a go, let's go through it. So we have 3 is greater than 2. Is there an equal sign here? There is not. So this is not an equation. Now looking at example 2, we are now going to start to get into solving linear equations. So looking at example number 1, we have 2x equals 6. Now, to first understand how to solve these, let's not solve them algebraically. Let's just think about how we could find the value of x without doing any algebra. So for the first problem, we have 2x equals 6. And x is some unknown value that we don't know. But little do you, maybe in elementary school, we were doing problems like this. What this is saying is, what this x is x is some unknown value. So what this is saying is, what do we have to multiply 2 by to get to 6? So 2 times what equals 6? That's what this is asking. What is the value of x? 2 times what equals 6? Well, that's 3, right? Because 2 times 3 is 6. So just by thinking about it logically, without doing any algebra, we know that x has to equal 3. Let's see if this logic holds true when we solve this algebraically. So to solve this algebraically, what you have to do is do the opposite operation of what's being done to x. So 2 is being multiplied by x. So to undo this multiplication, we have to divide. And we're going to divide by 2 specifically, so these cancel, and we're just left with x. However, whatever you do to one side of an equation, you have to do to the other to keep it balanced. Otherwise, if you don't do that, you're changing the equation, and you're like unbalancing the equation, and it's going to be a false equation like we've seen up here. So you have to make sure what you do to one side, you do to the other. Alrighty, so we cancel out 2, we get x equals 6 divided by 2. Well, that's 3. And that's our answer. And our logic from before does check out. So this does make sense. Looking at example number 8, we have x plus 3 equals 6. Now this does look a little bit different, but the same logic still applies here. So x is some unknown value, and we have to think to ourselves, what does x have to be so when we add 3 to it, we get 6? Well, that answer is 3, just thinking about it logically. X has to equal 3 because when we add 3 to it, we get to 6. Now let's solve it algebraically. Algebraically, we have to do the opposite operation. And in this case, we have plus 3. So the opposite of operation of addition is subtraction. So we're going to subtract 3 on both sides of this equation. These 3's here cancel, and we get x equals 6 minus 3. Well, that's just 3. And that's your final answer. And our logic does indeed hold true for this one as well. Looking at example number 9, I encourage you to pause the video and try this one on your own. Use the same exact process that we used for example number 8 for this one. And assuming you have given it a go, let's work through it. So logically thinking about this, we know that when we add 2 to some value, we get 6. So that some value must be 4, right? Just thinking about it logically, right? Because x has to equal 4 logically, because 4 plus 2 is 6. Now let's do this algebraically and see if it holds true. The opposite operation of addition is subtraction. So I'm going to subtract 2 on both sides. So we get x all alone. So these 2's cancel. And then we get x equals 6 minus 2 is 4. Well, our logic does indeed hold true. We have x equals 4, x equals 4. Perfect. Alrighty, so looking at example 10, we now have 2 steps to do here because we have 2 different operations. We have addition, and we also have multiplication here. So we're gonna have to do 2 steps here. Logically, we can think about this. It's a little bit more difficult because we have 2 operations. But let's see if we can go through it. So we know that this whole side of this equation equals 10. and we want to know this value of x. So logically, we know that if we add 2, we're going to get to 10. So 2x must be 8. We know that for sure. And if we do this algebraically, the first thing you have to do is do any addition or subtraction before you divide or multiply anything with linear equations. So we're going to subtract 2 on both sides. So you're going to get 2x equals 8. Now that we know that 2x must equal 8, we can think about this logically. What do we have to multiply 2 by to get to 8? Well, logically, we know that's 4, because 2 times 4 is 8. Let's see if this holds true algebraically. So because 2 is being multiplied by x, we have to divide on both sides to get x on its own. And we're going to get x equals 8 divided by 2 is 4. And our logic does indeed hold true. Looking at example 11, I encourage you to pause the video and try this one on your own. And assuming you have worked through it, let's go through it together. So we have 2 minus 4x equals 10. So we know, as I stated before in example 10, to solve a linear equation, you first have to cancel out any addition or subtraction. So looking at this, we have 2 minus 4x equals 10. Now, some of you might see this subtraction and say, oh yeah, let's add 4x here. But in this case, I mean, you can do that. But in this case, in terms of keeping things at least kind of more simple for this first section of notes, I would just keep it as it is. What I would do, you always, when you're solving for x, think of it as like this. You always want to start off by subtracting whatever's furthest away from x. So because this 2 here is farther away from x than this 4, we're going to first want to tackle this 2. So to get rid of this 2, I'm going to simply subtract 2 on both sides. You're going to get negative 4x equals 10 minus 2 is 8. And then now, this negative 4x is being multiplied by x. So to undo this negative 4, to get x on its own, I'm going to divide by negative 4. So we get x equals 8 divided by negative 4 is negative 2. And that's your final answer. Looking at example number 12, I encourage you to pause the video and try this last example on your own. And assuming you have worked through it, let's go through this together. So we have negative 15 equals negative 3x plus 2. Well, as we've seen in the other examples, we first want to tackle what's furthest away from x, or we want to tackle addition and subtraction. And because we have an addition here, we're adding 2, we first have to subtract 2 on both sides. So we have negative 15 minus negative 2, that's negative 17, and that's equal to negative 3x. And now that we have negative 3x, and this negative 3 is being multiplied by x, to undo this negative 3, or to get x on its own, we're going to have to divide by negative 3 on both sides of the equation. So we get x equals negative 17 divided by 3. Well, that's not a whole number. But what we can do is recognize that a negative divided by negative is going to be a positive number. So we're going to change that negative 17 over negative 3 to positive 17 over 3. And that's your final answer.